Okay, good afternoon everyone. My name is Kevin. Everyone can hear me good?
Yeah.
Okay, great. Yeah, so as the title suggests, I'm going to be talking about my project, which is looking through walls with artificial intelligence. And we'll get into what exactly that means in a second. So to sum it all up, this project is about seeing the human figure through walls. And the human figure is basically, for us, a 15-point skeleton. So first, a little bit about why we might want such a technology. And the idea is that saving people and seeing people through walls for good reason or bad has always been a dream of ours, right? If you guys have seen the 1987 Robocop movie where he busts through the wall and then gets the criminal and then beats him up or whatever, that was one of the inspirations for this project, among other things, like video games or books or movies that you watch. So that's always been a dream, and to kind of accomplish this dream, we can't rely on the normal visible light, right? Because as we all know, this wave, it doesn't go through walls. But interestingly, a wave that we traditionally view as a communications wave, radio frequency wave, can be harnessed for imaging. Now, usually it's not thought of as an imaging wave because of the many physical properties and challenges that we'll face when dealing with radio frequency, but it is able to go through walls, and that's really what we're looking for here. So although visible light can't penetrate walls, radio frequency can, so that's what we're going to harness in this project. And in a couple slides, I'll kind of get into 3 really killer applications that I think are especially exciting for this project. So let's define a kind of a more specific goal, a more formal goal. So the idea behind this project is to establish some kind of methodology, it just happens to use artificial intelligence this time, to convert radio frequency images, or essentially radio frequency reflections off of people, into a human figure. Now, what is this human figure? It is simply a skeleton, a 15-point skeleton that defines all the key points on the human body and then links them up. So once you have this kind of information, you can do things like gait analysis or fingerprinting even, possibly. So that is what we're going to be looking through walls. So you have this radio frequency imaging device. You can think of it like a camera, but for radio frequency. It sends signals. Some of them get reflected or absorbed by the wall, but a lot of them also go through and reflect off of this guy. We'll call him Joe for now. And Joe is seen by this device. It gets some information, but this information is initially very difficult for humans to understand. So we're going to be using some deep learning methodologies to deal with this information and then process it into something that we do understand, which is this human figure. Now, a couple of goals for this project. Number 1, we want it to be able to handle different obstruction structures. It's a given, right? You need to be able to go through walls, drywall, insulation, wood, brick, paper, things like that. Also, we want to be able to process multiple people, because rarely ever in the real world do we only have one person that we're targeting. And then third, we want to be able to execute this thing in real time, or else it's not going to be much of a use, for example, in military situations, or even in other situations that require online processing. And then finally, safety and health. This one is actually a little bit of a less of a consideration on my side, because the radio that we use is FCC approved, and it transmits signals at 1/1000th the power of Wi-Fi. So we're good on that for now. So those are some of the requirements or the goals that we want to achieve. And then finally, we explore some alternative solutions or related works. So the story goes is that about 10 years ago, people from MIT, they started investigating this idea of using radio frequency signals as an imaging wave in addition to a communication wave. And so 10 years ago, they started developing hardware for this. They started looking at the different physical phenomena that occur when you try to use RF as an imaging wave. They tried to address that, and then in 2015, they released some traditional rule-based algorithms to try to patch together different body parts as they show up. And I'll get into what exactly that means in a second. And then recently, they've started using deep learning, but then sometimes they leave some considerations out, so that's what we're going to try to address in this work. And we'll get into exactly the details of that in a second. So that is the high-level overview of what this project is about. This one's not really that interesting. These are some materials very typical for such a project. I guess what's notable is, number 1, of course, we're using Python in these deep learning libraries. I used a GPU server that a friend so graciously lended to me. And we're going to use some hardware devices, namely a web camera, just a regular camera, and then a radio frequency imaging device, an antenna array, and then a single board computer. This can carry out these computations in real time, but with a little twist, which we'll get to in a second. And then finally, a tripod mounting stand for this thing to actually take physical form.
So let's get into the process. We're going to start out with the device sensors. What exactly we need to collect information that we're going to be processing with our deep learning methodology. So first of all is the radio frequency transceiver. It is this, have you guys ever heard of Wallabot? Just curious. Okay, no. Well, they produce commercial grade imaging radio frequency antenna arrays. Essentially the idea is they transmit RF signals, they receive them, and then they receive two important pieces of information. Number one, where reflections come off from, the spatial direction, and then second is the distance. So with that, you can have an idea of everything that's in front of you, right? Those are the dimensions that we need, space and then distance, well, angular space and then distance. So there are several parameters. This transmits on the bandwidth from 3.3 to 10 gigahertz, so it avoids the Wi-Fi at 2.4. It's a little bit higher than that. But the key property that we're looking for here is that it can traverse walls. I actually tried experimenting with different kinds of waves, for example, millimeter waves. But I mean, with the rollout of 5G, we all know that those have much weaker penetration capabilities than these kinds of than waves on this kind of frequency. And of course, I kind of talked about this earlier. It's 1/1000th the power of Wi-Fi. So if we wanted to go longer distances, we can tweak that, increase it a little bit. And then finally, because of the physical properties of RF antenna arrays, of course, they image on the spherical coordinate system, and we'll have to deal with that a little bit later. And just for reference, this radio frequency device is as big as my cell phone. It's about 6 inches, 6.5 inches on the diagonal, so not very large at all. And of course, if we had some more demanding tasks, we could also increase the size of the array. So second, we have an RGB camera. Now you might be asking, wait, we're looking through walls, why do we need a camera? And the key part of here is we need to teach the model how to see through walls. And this will become important in a moment, and I'll explain how it factors into everything in a moment. And then finally, we co-locate these devices. So what you might gain out of that is, so we're going to try to collect information in parallel. Number one with radio frequency, and number two with regular color images. And this will help us train the model to be able to see through walls. So this is kind of the co-located setup that we come up with. These are fixed relative to each other. Okay, so those are the device sensors. Now we need to acquire some data, right? So let's talk about the two sections. Number one, the radio frequency, and number two, the RGB, the regular color cameras. Let's just call it the color cameras. So first of all, I kind of touched on this earlier, but the key question is, why are we using radio frequency in the first place? And the simple answer is we needed to be able to penetrate walls. So I've just ripped off a picture off of Google. This is the electromagnetic spectrum. And I've highlighted this section in which you have very good penetration capabilities. But there is a trade-off. If you make your wavelength too long, then your imaging becomes much less detailed, right? It's just another trade-off that we have to deal with. But the key thing about radio frequency waves are in this kind of Wi-Fi cellular band is that we know from empirical experience that these penetrate walls very nicely. And also, based on additional research, these also bounce off of humans at quite a reliable rate. So these are very good for I guess you could say, the best version of the radio frequency spectrum, the best kind of slice that we can. So penetrable materials are wood, brick, drywall, concrete, so etc. What you would generally think of as wall structures. And then, yeah, we kind of observe that if you increase the frequency, you increase the resolution of your imaging. However, you decrease the penetration power. So that's a kind of a balance we have to hit. So this is a very brief overview of the workings of this antenna array. And there are two key components. Number one, we need to be able to determine where signals are coming from. Are they coming from left, right, up, down, or whatever the other directions are? And that can give us an idea of spatial direction. But with that, that's not enough, right? Because we also need to know how far you are. So traditionally, you would think of simply saying distance equals speed times time. But the problem is that these waves travel so quickly at the speed of light that it's very, very difficult to measure the delta t. So what people actually do is they use this technique called frequency modulated continuous wave, in which they don't just transmit a signal and then try to capture the exact moment that it comes back. They actually modulate this over time. They modulate it linearly they modulate the frequency with respect to time in a linear fashion. Now what happens now is when you send a signal, it goes like that, and then when it comes back, it's kind of shifted, right, on the time axis. So it comes back here. You can measure this delta F very, very easily with a hardware device. It's even a passive device called a mixer. Now this delta t is extremely hard to measure. So, but if you have this delta f, you can simply use the slope and then compute the time, right? So that makes things very, very easy. So now that we have the spatial and also the depth information, we pretty much have a 3D distribution of the reflection power from every point in a kind of like a space in front of you, right? You have information for each voxel, how much reflection power is coming back to my receiver. So that is essentially an image, right? We have ourselves an image. So interfacing with this antenna array, there's an SDK, there's an API. What you can do is you simply call the radio and you tell it to sweep, and it gives you a big cube, a big volume of reflection powers. So if you have a person here, you take the device and you send and receive signals, and you get something like this. You get it normally in this rectangular prism type of shape, and that's in spherical coordinates. And of course, we want to represent space better with Cartesian coordinates because we're going to do a little bit of pre-processing later. So we convert it into Cartesian coordinates. Anyways, the representation is just a matter of converting. This is what we get. We get a 3D distribution of how much reflection power we have in front of you. And then in the additional side, we have the color camera that's collecting direct video of this person that's walking around that only is needed in the training phase, and I'm about to get to that. So together, we have the antenna array and the web camera. The antenna array logs in CSV files, the data directly comes from that, but the camera comes in MP4 files, so we're going to have a couple of challenges in dealing with that in a second. So first of all, we have a little bit of data pre-processing. Essentially, we want to convert to Cartesian coordinates, and here's a justification for that. Operating over dimensions, we have 3 dimensions of space and then time. 4 dimensions is notoriously infeasible when you're looking at convolutions, for example. So what I want to do is to kind of summarize this 3D information without regard to time. We want to summarize this 3D information in 2D information. So this is something that other people have done before. Essentially what they do is, imagine like a flashlight, right? You have a flashlight pointing at me, and if you point it at me from this direction into the page, you have a shadow on the wall. That is essentially what I call a vertical heat map. And if you think about it, if you take a flashlight and point it at the wall, you can see my features, right? You can see where my head is, where my shoulders are, etc. So you have that kind of information. And then the second piece of information is, for example, you have a flashlight on the ceiling pointing down at me. Then if you imagine that the floor is a plane where the image lies, then you have information of where I am. Am I here? Am I here? Am I close to you? Am I far from you? Am I on the left? Am I on the right? So in this manner, we can kind of summarize this 3D information succinctly in 2D form, and we can make computations much, much easier with that. So that's the idea behind the pre-processing. So now that we have all our data, we need to take a look at some challenges that we might face. Because if you actually take a look at the radio frequency images, you might think, without actually looking at the images, you might think, we already have the images. Why do we need this AI, you know? And let's get to that. So if you take a look at this picture, this is a radio frequency heat map, and we're going to focus on the vertical side because that's where the problems actually arise. This is a vertical heat map, the flashlight pointing at me. Now you'll notice this is at time t plus 0.2 seconds, and then t plus 0.4 seconds. Where did his body go, right? Initially you can kind of see his chest and his arms, etc., and where the legs, but you see his feet, and then just a fifth of a second later, most of his body is gone. And you can kind of see the chest is always there because you can think of it, it has the largest surface area, right? But why is this? The key problem here is a problem called specularity. And this arises from the issue of using radio frequency. Remember, we said there were going to be several drawbacks. One drawback right now is that radio frequency's wavelength is about 5 centimeters, whereas visible light, we all know, is about like 500-600 nanometers. That's a very big difference. So what happens is, when your wave that you're imaging with has such a long wavelength, you appear very smooth to it. It doesn't see a lot of detail on you, or any objects for that matter. And what happens when things appear smooth, they follow the law of reflection. So if you imagine a radio receiver here, it sends some signals, and imagine this is like your arm, for example. Your arm is here, it bounces off that way with the angle same, incident and reflected. So if your radio frequency receiver is here, then the waves go that way. this is equivalent to being invisible, right? Invisible is when the waves don't come back to you and you can perceive it. So that is the problem that we're seeing when you move and then your limbs are not at the right angle. As close to normal as possible would be ideal, right? They're not close to normal, so then the waves are coming in this way and going off that way and you don't see it. So that big problem called specularity is what we're going to be dealing with using deep learning. So several challenges that we're going to be facing in addition to this problem of specularity is number one, low resolution imaging. Because we have radio frequency, of course, inherently it's going to be less full of information. Second, we're going to have multi-person support, which is a challenge because these radio frequency waves they're kind of unpredictable at times. They can maybe people can interfere with each other. Some person can walk in front of another person. And for example, if you have person A and person B and then they switch sides, who is who, right? So these are all problems that we need to tackle with multi-person support. And then finally, of course, body part specularity. So this low-resolution imaging problem can be solved with convolutional neural networks. We can use them to analyze these heat maps and then extract information from them. Second, multi-person support we can solve using a region proposal network, and then we're going to use a little trick to be able to track people over time. And then finally, third is a recurrent neural network. So this is the interesting part. Let's think about it. We have body part specularity. And so what we've noticed is that at times you don't see the person. Now we can exploit motion and we can exploit time. Because with the passage of time, it doesn't matter how to a little of a degree that you move, but you move. And when you move, different body parts can reflect signals back to the receiver. So if you notice, if you accumulate information from time A and time B, they were only very recently, if you synthesize information over multiple time steps to see which body parts were reflecting back at different times, you can kind of infer the pose at time C, right? So that's the idea we're going to take with the recurrent neural network. You analyze what happened in time A, you analyze what happened in time B, and so you synthesize these pieces of information into time C so that you can produce a more complete pose. So that's the idea behind the recurrent neural network, which is a temporal model. And so that's what we're going for. So let's discuss a little bit more of the details of the architecture. This one is quite standard. It's a residual convolutional neural network. Essentially it is, you feed it these images and it extracts information about, for example, where the limbs are, where the hands are, where the head is, etc. So then you have these features, and then we simply add a state-of-the-art model called the residual convolutional neural network, which has jump connections that allow it to serve a better fit to the data. And in some cases, we can see that it overfits data less, while we even have more layers. So that's one of the architecture choices for the convolutional neural network. Second, we have a region proposal network. And what you can think of this as is, if I give you a picture of something, you tell me where the person is. We train it to do so, except it operates on the outputs of the convolutional neural network. So we're basically stacking models on top of each other. And then finally, once we have all those region proposal network proposals, we hand them to high confidence proposals, of course. We hand them to the recurrent neural network. So this is actually the key of the study. This is the key, and what I like to call it is a many-to-many architecture. So you want to output many frames of continuous video of this person's pose, but you also, to create all these many outputs, you need many inputs, because we want to accumulate information over time, hence exploiting the passage of time, right? So the long short-term memory network is, of course, the state-of-the-art in many temporal modeling tasks. And in this case, it is going to be good for our task because we need to consider information not only from the current time step, but also information that has come before us. So that's the intuitive justification behind using the RNN. So this is kind of a summary of the model, right? You have input radio frequency images over time. You can just think of these as like a low frame per second, a low refresh rate video, a bunch of different frames. So you pass each of these frames through a residual convolutional neural network, which shares its weights. It uses the same weights each time. It extracts features. It passes these feature maps to a region proposal network, which defines where these people could be. And then you output the high confidence proposals to a long short-term memory network, which accumulates information over time. And so after you get this hidden state output from the recurrent neural network, we want not 1, but we want 15 points, right? And so the idea behind that is we have in a recurrent neural network, after it processes all that data, it outputs a vector of numbers, just a couple of numbers. So we have 15 different sets of weights that we apply on top of that hidden state output to get these 15 points. So you can think of it as, at the current time step, I have this vector of information that encodes the state of the person, and then we apply 15 different processing tasks to extract specifically where the head is, where the shoulders are, etc. So that's essentially the end-to-end model, and then we can train all these weights jointly. Okay, so that is the training part. But now, if you may be thinking about this in your own mind, you may ask, this is a supervised learning task, right? So where are the labels coming from? That's what we're going to be tackling here. Because remember, if we have these input images, where are these output labels that we have to compare our outputs to, right? We have none. So let's explore a couple of options. The first option is that you could decide to, hey, I can label these things myself, right? So for each frame, I label 15, and then for each segment of video, I have like 20 frames, and then I have thousands of these. Yeah, it adds up pretty quickly. So that's not the solution we're going to be going for. So to solve this, we use a nice trick. We kind of ask a second teacher AI model to help teach our student. So that's where our camera comes in. And let's show this image, because I think this explains it pretty well. So instead of just having a radio frequency device, we add a camera. And what's interesting about cameras is that, of course, they're so high resolution, but they don't go through walls. But let's not dwell on that for now. We want to focus on their high resolution, because right now, a lot of state-of-the-art performance has been achieved in extracting poses from people. Like if I have a picture of myself, it'll say, hey, here's the head, here's everything. Here are all the data points, and it's also extremely accurate, and it gives you all of this information through an API. So you can have this, you can have these two channels of information coming in simultaneously, and you split them into two kind of processing streams. Number one, we have a teacher model, and you can think of this teacher model as a gait analysis module. It takes in color images about the person, and it tells me where exactly are the parts of the body that we're looking for. And this teacher model is very good at its job. It's already been trained, so we can treat its answers as the ground truth, or the correct answer that the teacher provides for the student. So now in the second parallel, it's happening in parallel. You have a student see-through model that's taking in only these RF images, and it's saying, hey, what do I think the pose looks like, right? And it goes through all these processing components and it forms its prediction. And the teacher can either say, hey, you're right, or hey, no, you're wrong, please get better. So the student takes both of these inputs and then it learns to correct its mistakes using an intelligence mechanism called backpropagation, essentially to minimize the difference between its answer and the teacher's answer. So this is how we're going to overcome the problem of no labels, by asking a computer to do the labeling for us, a computer that's already good at its job. So now there's one final question, right? You have a camera. The camera doesn't go through walls, so how can you explicitly train this model to go through walls? And to that, we simply add an obstruction. We just get some materials, and then we put it in front of the radio frequency device, but we don't block the camera. So the camera can tell us where this person's body parts are, but we can also simulate the attenuation and the noise that's added to these signals when you have that kind of obstruction there. So in that manner, we can explicitly train through obstruction, instead of just having this happen as an accident. Which it has in the past, because MIT's work, if you've ever heard of RF pose, their title was looking through walls, but actually, if you read the paper, they said that this was only an accident, that it just happened to be that this could generalize to the through-wall case. But of course, their performance is going to be as good as if you directly train it through walls, right? Just intuitively. So these are the things we just kind of talked about. The AI teacher provides the correct answers, the student generates its own answer, it learns by rectifying mistakes. And then once we're kind of like teacher B, or like we're the pseudo teacher, we can tell the student, hey, you fulfilled your graduation requirements and you can get out of here. So now if they don't graduate, we can continue learning, or otherwise we can stop training and we can start using it. So we kind of talked about this too. There's a training pipeline with artificial obstructions, and this is kind of a diagram that shows you what that means. You don't block the camera, but you simulate the blocking of the radio frequency device. And so now we reach a problem of the loss function. Essentially what you can think of this is as a grading scheme. How stupid is your student right now? And traditionally, the way that this problem would be traditionally formulated is you have a bunch of output neurons. Essentially, you have, let's just say you have 15 body points, right? Let's just focus on one body point for now. So for each body point, we want to classify this person's body point into a pixel on an image. For us, that's 32 by 64. Sorry, it's 48 by 64, sorry. So you have this 48 by 64, so you can think of each key point, each of these 15 key points has 48 by 64 output neurons that the neural network says, hey, which one of these is the correct answer? As you can imagine, that doesn't sound so great, right? We don't have a lot of data and we have so many weights, it doesn't sound like a recipe for disaster. So to kind of alleviate this problem, we introduced a more intelligent grading scheme. So generally, or if we didn't make any modifications, a misclassification that is close to the ground truth would be equally penalized as a classification far from the ground truth. For example, if you're trying to classify my face and the ground truth is right here, and the model says it's somewhere, it's at that TV that says 7-Eleven right now, that's bad, right? But that would be met with the same penalty as if the model classified their prediction to be right next to my face. So what we do is we introduce this loss function and we say, hey, we want to minimize the students who are making the worst errors first. We want to bring them up to par, and then we can fine-tune later. And the way we do that is we introduce an exponential term to this loss function. We say that your penalty increases exponentially with the distance from the ground truth. So this is a way by which we can encourage the model to reduce overfitting by trying to focus on the ones that are already close, by pulling in the things that are very, very far. So that's the idea behind this objective function. And of course, this backpropagation algorithm is very standard. It's gradient descent, of course. And this is a little bit of information for about the data set. This was collected by me because there's no public data set for this. There were 5,000 training samples that I cut up and augmented into 75,000. So they were collected at different areas. Most of them were collected at home. So we have different kind of actions. You can note walking, gesturing, sitting, and there are also my dad and I, we join in some of the data points. And also something to note is that there is one that's called no person. And this is kind of the problem that we're seeing, is that maybe sometimes these models will try to find people when there's actually no one there because of the, for example, the noisy environments. Like these chairs could reflect signals back to me. So this is just to tell it, hey, don't classify it into a person if there's no one there. We tried multiple mediums. There were 5, 1, 2, 3, 4, 5, and open air is the kind of, I wouldn't say control, but it's just the one that's regular. Wood, brick, drywall, plastic, paperboard, and then open air. And then as in standard practice, we split it a 65, 5, and then 30 for the training, validation, and testing sets. All right, so now that, imagine we've already completed the training, we're almost through, because now we can finally do reconstruction. We can get rid of the teacher because the model already knows how to do its job, so using only radio frequency signals, it can output a prediction, and this prediction is hopefully very accurate. And a couple of applications that we'll get to for this are actually quite interesting that I thought of, that we'll get to in a second. Okay, so now that we have this reconstruction, we have it in offline processing, but we have a problem now. If you want to use this in the field, you want to use this in military, you want to use this in healthcare, how do you get this to run in an online fashion, where it gets data and then processes it live? So the problem is that this requires a lot of computations, and we don't want to be carrying a GPU on our backpack. So what you might think of is we use a Raspberry Pi, right? A very standard DIY hacker kind of tool, but it's not very powerful. In fact, it's actually quite poor in terms of compute that we need. But that's okay, because we're going to design a system in which it uses the internet. The internet can send information over a connection and then get it to the GPU server, it computes the pose on there with a preloaded model, and then it sends it back over the internet. I actually tested it, and very just regular LTE speeds are able to handle the demand. I actually just set it to forward through my home Wi-Fi network to this thing, which is actually on the second story of my house. So my internet's not the fastest either, but it does seem very viable because the information that you're sending is not really great in volume anyways. So this is a method by which we can circumvent these problems of needing excessive compute right by your side. We don't need it anymore. We can simply use a Pi and then send it over the internet and offload that task. So now we get to the killer applications, and I think there are 3 that are quite interesting. Number 1 is healthcare monitoring, and this was actually something that inspired my project. Because a lot of the times when we want to monitor the health of elderly people, right? We want to, for example, put cameras there. There are several problems with this. Number 1, privacy, right? There is a reason why we don't put cameras in the bathroom, but the bathroom is also one place where people can slip and get hurt. And patient privacy, that's the key issue, right? We don't want to be able to see everything about the person and collect this information that we don't actually need. Second is key point location, because if you find, let's just say that we improve the privacy, now we need enough detail to actually be able to do something with it. And so that's the kind of the trade-off that we explore here with looking through walls, because when you look through walls, we don't see everything about the person. We don't see when they're showering, we just see their 15 key points. And to a certain degree, that retains a little bit of their privacy. But the important part also is that you can still have these key points to be able to do things with. And this is actually quite powerful in my opinion, because you can do things, for example, you put these 15 key points through a second auxiliary model. You can track their gait, and gait analysis can be used for many things. You can fingerprint people, you can track them, you can even analyze their behavior, you can, and interestingly, for gait-degenerative diseases like Parkinson's, you can analyze their gait and perhaps notify people when you see signs of it. So this is very interesting. And then finally is through-wall imaging. When you have someone that's in a dead zone, because cameras, there are nooks and crannies everywhere. If they walk behind a wall, what do you do if you can't go see through walls? So that's another elimination of dead zone that's also quite important. And also another one is fire search and rescue. This one's really interesting to me, because traditionally infrared doesn't go through fire, it's the infrared fire, right? And then there's also visible light, which doesn't go through smoke, doesn't go through fire. But radio frequency signals can. And interestingly, they can then help first responders locate these people through walls. Finally, this one's kind of straightforward, and this is the Robocop example we talked about earlier. Law enforcement, if necessary. Okay, so now we're going to take a look at briefly some results. Number 1 is an analysis of, is this thing useful? Seeing in free air, not very useful to us, but it's a good benchmark because that's how we train the model. And then second, we have gait analysis. That is not necessarily, that's not our thing, but seeing through walls is not possible with radio frequency, with RGB, not with visible light. So what we have here is radio frequency, which is able to do it. And in these interesting kind of use cases, this can be very helpful. So this is just a training plot. It's essentially how well it did, and I guess the key takeaway here is that the validation data only has a little bit of a difference with the training data, so you know that it's not overfitting too much. So that's the purpose of the validation data set. Okay, so now we reach a problem. How do you evaluate the accuracy of these data points? Because I think it would be rather harsh for us to say you have to classify to the exact correct pixel. So traditionally in other computer vision tasks we use IOU, right? Basically the overlap. But points are one-dimensional, so what is the IOU? It's either 1 or 0. So we borrow an idea that was actually evaluated, that was used to evaluate computer vision tasks that deal with RGB images, and it essentially constructs this distribution and it's centered at the ground truth. And then you evaluate this. X-axis is your distance from the ground truth. And you evaluate it on this curve. It's not normalized, so the maximum is 1, the minimum is 0. And then the the value of the function at that x value, left to right doesn't matter. It is your performance. Let's define that as the key point similarity. So the key point similarity, just for reference, if a human was to look at a picture of me and try to locate all the body parts on my body, 95% of those key points will have key point similarity of greater than or equal to 0.75. So as you can imagine, this is a 75 is quite a strict match, and a 50 is a medium match. And then average accuracy, these are just some definitions because this is a new way of evaluating stuff. Accuracy we can define as, let's just say we have a key point of the shoulder, right? And it has a key point similarity of 0.4. We can set a threshold to say, above this threshold, you have successfully classified this correctly, or to the best, to our demands. So if it's 0.4, it would be a 0 if our threshold was 0.5, right? Because it's not to our standards. So accuracy is the proportion of the key points that have a key point similarity of greater than or equal to a threshold. So those are some definitions. Now we can take a look at how this thing performed. So these are the individual key point classification errors, and they're grouped by body part, by head, shoulder, elbow, hand, feet, knee, hip. I think those are the ones. Okay, so this one is in general, classification results for all key points. So you can see that 64 plus 30, 94% of them were classified with medium or lower errors, which is interesting. But also if you look into specifically what is being misclassified the most, let's see, misclassifications. It seems like the feet are misclassified very readily, and also the hands. I guess you can imagine that because the feet are on the ground and the hands are quite small. So those are some interesting things we take away, but in general it performs quite well. And this is the average accuracy. This is when we group it over all of these people and then see how well it performed. So this is a key point threshold at 0.5, and this one is 0.75. And then the blue bars are for visible scenes, and then the orange bars are for through obstruction, or like occluded scenes. Of course, when you go through walls, it's a little bit less accurate, but it's interesting how the drop-off is not that quite significant. And again, we see that feet are classified a little bit lower, with a little bit lower reliability. So now I wanted to evaluate what happens for this, what happens when you compare this against the state-of-the-art vision model. Now, I don't think there's anything to talk about here. I don't even know why I added this graph. But when you go through obstruction, of course, it's going to be 0 for the RGB. But what I actually found was, interestingly, when you have a very low, key point threshold. So what you see on the x-axis here is a key point threshold, and then this is the accuracy. So we're evaluating the accuracy at different key point thresholds. So the very left right here is 0.5. That would mean very, very medium kind of level match requirement, and 1 must be exact. So as you can see, the blue line represents the radio frequency, and this orange line represents a tool that I downloaded off of Microsoft. They have a similar pose classification detection thing. Interestingly, at very low thresholds, the radio frequency thing does pretty well. And I have some intuitive explanations, but I don't know if they're correct. We can infer, right? First of all is the new objective function that reduces overfitting. That's important because we don't have that much data. And then second was the many-to-many imaging with long short-term memory. I think that's important, that you're accumulating information over time. So second, the observation that we have is even for through obstruction inference, we only see a slight decrease in performance. So that's a good sign. And then finally, we have some analysis on the media. What happens to your classification when you go through different materials? Of course, okay, dang, paperboard was really high, but then you see it kind of decrease as you go down to the more dense materials like brick. And of course, it doesn't go through metal. Okay, so that's pretty much everything. So we kind of discussed, number one, selecting a wave to actually accomplish this, and then we talked about kind of formulating some methodologies using machine learning to deal with the physical challenges that come with this wave, because everything has pros and cons. So some of the contributions that are from this project is this new AI model. That's, of course, the highlight. So the residual convolutional neural net is one part of it. There's a region proposal network that in implementation, we can talk about a little bit details later, but the region proposal network for multi-person support and then integrating that with the long short-term memory required a little trick. So these are the three big contributions, and then there's an objective function that we use to reduce this problem of overfitting There's a new training pipeline, and then we have a new data set that I'm planning on releasing soon. So yeah, that's pretty much it. And then finally, I have for you guys a demo. And we'll talk about future work later. This is a demo. This is a, I know you guys can't tell, but this is a 15 centimeter thick drywall. You can't tell because this is triangular shape, so we're on the wrong side of it. You won't see it. It's a trapezoidal triangular shape on the side. But you can see that this is the radio frequency device going through, and then there I am on the other side. This camera that you're looking at this scene through now is only for visualization, so that you can see that these poses are being produced correctly. So this is actually the pose that comes out of it. And these are the, you're not supposed to be able to read these numbers. This is just to show you that it's these are actually specific points that are coming out. These are the weird pictures that are going in, and this is the confidence. Sometimes it drops pretty low, but that's just to show you when things are confident and when are not so confident. Oh yeah, this was a video that I filmed when I was in Phoenix for the competition. I actually realized that they didn't allow Wi-Fi, so I went to my hotel room and I had my friend help me film this video. I know it doesn't go through walls, but I just wanted to show the setup with Pi working. So yeah, that's pretty much it.